we're going to talk today about algorithm metrics that are appropriate for our detection algorithms. We have detection algorithms. They are listed here that we sell commercially today. So just something that's out of scope today. We're not talking about CT perfusion, RV-LV ratio, or any of our future products that will include measurement like ICH plus or SDH plus. Those actually measure something versus actually detecting something present or something not present. So this is about detection. I have a comment on the side here. We're always working to improve these algorithms, working to improve our sensitivity, our specificity, et cetera. Today, LVO is on version 16. So we've actually done many releases since initially building that particular product. Before I get started, I wanted to talk a little bit about how we build algorithms. This is super high level. This is supposed to be around a 15, 20,000 foot view of how algorithms actually get built, but it does help to understand why we may actually see a difference when we go to market with a product and have it running through real customer data versus the training data and validation data that we use today. So in general, for algorithm training, as an example, we might actually try to acquire 1,000 positive patients and 1,000 negatives and the imaging that goes along with those patients. So we may start out with these 1,000 cases, and these are used for training the algorithm. What does the disease look like in this imaging? What does it not look like? And it takes a long time to do this, and the algorithm engineers do this sort of steadfastly against each individual CT that they receive. We obviously are looking for a robust and diverse training data set, but it would be impossible and implausible to have it be representative of everything that the algorithm will ever see. From there, we acquire a smaller data set for validation. So this is not allowed to go into the training data set. We actually need to run the algorithm against data that was not used to train the algorithm. That would kind of be cooking the books. It probably makes sense. We would expect almost 100% sensitivity and specificity across our training data because we used it to train the algorithm. That is analyzed by a third party. So we're not allowed to say to the FDA, hey, we did great on our validation data set. It needs to be by a neutral third party. We pay for this to be done. And we're looking to hit certain performance metrics depending upon the clearance pathway that we have. So when you see like those 92% sensitive and 91% specific, we're trying to hit a particular value in order to get into a particular clearance pathway with that algorithm and also have it be valuable to users. When we meet that metric, we submit this to FDA. And then over time, we start building a testing data set. What that testing data set allows us to do, this is generally with real customer data as we start to go live, is it allows us to validate both the existing algorithm as well as future iterations of the algorithm against what we would call real world data, the real data that we expect to go through it. What happens? Every single algorithm we release and have released has experienced data drift. They all drift one way or the other. And it's because we end up getting diversity of data that is not represented within our initial training and validation data sets. That will happen every single time. It might happen with the first customer that goes live. It might happen with the 20th customer that goes live. It might happen when we have 100 customers live where we just get something that we've never seen before, like a customer upgrades to a new scanner, uses a new protocol, et cetera. And this inevitably will happen. The great thing about that is we're able to leverage that data oftentimes to further enhance the algorithm. It can be a treasure trove. The only negative to this is that it oftentimes takes time to do this, which is very challenging, depending upon how much time that may take. So we're going to go through a series of definitions today and have some exercises to boot. I think this will be fun for everyone. I hope you can get involved and participate. We're going to have people put answers into Slack as we go, but I'm also going to try to keep the pace moving forward quickly, ideally to get through the material that we have today. To start out, what the heck is ground truth? You guys probably heard of it before. There will not be a calculation for ground truth, but I want to level set. Ground truth is not whether or not a patient was found to have a disease after an autopsy, right? This is ground truth from our perspective is if the disease was actually visible, possible to detect in the imaging that's going through the algorithm. So in the case of LVO, could it have been seen by a number of radiologists looking at the same image or not? That would be establishing the ground truth via a multi-reader study. And that's usually a yes or no. So it's not usually one reader, but it will be multiple readers to establish that ground truth on a particular algorithm. That is our holy grail that we're trying to match our algorithm performance against today. So in essence, our ground truth is typically based on consensus reading. That means more than one person agrees that the disease is present when they look at an image. multiple experts need to independently agree on this. So when I talk about yes, there is a disease or no, there isn't, I'm always talking about ground truth and not whether or not it was proven the patient had a disease after the fact that was not visible in imaging. So beyond ground truth, we're going to jump into sensitivity. Ground truth plays into all of these metrics, which is why I wanted to talk about it first. Sensitivity, we talk about all the time. We use it frequently with customers, and it actually is probably one of the more simple metrics to explain when you really think about it. In essence, sensitivity is the proportion of people with a disease that have a positive finding. So to put this simply, if we were 80% sensitive, we would find that we would be finding 8 out of 10 patients that have a disease. 50% sensitive would be finding half of patients with a disease. The proportion of people with a disease that have a positive algorithm finding. A higher sensitivity means we're finding more of those patients. A lower sensitivity means we're finding less of those patients. And the calculation for sensitivity is actually quite simple. It is the true positives divided by the true positives plus the false negatives. It sounds a little bit confusing when I start using the terminology of true positive, false negative. But just understand that that bottom line below is all patients with disease. So the number of true positives divided by all patients with disease, in essence. So I'm going to start out with a scenario, and we're going to use this scenario over and over again, walking through a number of metrics. I'm going to read it once, and then beyond that, we'll just show it on the screen. So we have 20 patients that have been screened for a large vessel occlusion. These are all going to go through an AI algorithm in this particular case. It could be any disease, but we're going to focus on LVO here. According to the ground truth, so that would be those reader studies, 4 of these patients actually have an LVO. So those are 4 that would be diagnosed later in a radiology report, where all radiologists agree unequivocally that 4 of those 20 patients actually have an LVO. We have a magical AI algorithm that runs that's used to screen patients, and that algorithm generates 6 alerts. Okay, so 6 alerts are generated by the algorithm of suspected LVO. And these are going off on people's phones, and maybe they're flagging the radiologist of the suspected disease. Out of the 6 alerts, based on the radiologist analysis, 3 of them are true positives. So they are patients that have an LVO, and 3 are false positives. They do not have an LVO. Lastly, as you can see, I said 4 patients actually have the disease. So clearly 1 patient was missed by the algorithm. Now, I have a small grid here, and I'm hoping everyone can get out a pencil and paper if you have it, or have a little spot on your computer and actually try to fill in this chart, because these 4 data points will be used for every single calculation that we do. The number of true positives, the number of false positives, the number of false negatives, the number of true negatives. And I'm going to give the group 30 seconds to fill in their own before we show the next slide, which has the answers. I will give you a hint. It adds up to 20. Okay. Well, a couple of these are really easy because they're right there above. And there's one number that wasn't right there above that I hope you're able to pretty quickly get to. We said right in the description that there were 3 true positives and 3 false positives. So we have those 2. What we have here is a disease column. So the disease column represents patients that actually have the disease, according to the ground truth. A no disease column, these are patients that do not have the disease. We have findings for all of these patients. 3 true positives, 3 false positives, 1 false negative, and 13 true negatives. I hope that most of you are able to get to those same numbers, and those are the numbers that we're going to use in every calculation that we do after this point. And are you ready to try to use these numbers? I'm imagining hearing everyone go, yeah, let's do it. This is really exciting. I can't wait to use these numbers. Woohoo! Thanks, Susanna, for staying on camera. It helps to have that visual feedback. All right, so let's try to use them here. What is the sensitivity of our AI algorithm? We have all the data points that we need to put into an equation. Sensitivity equals the true positives divided by the true positives plus the false negatives. And I'm going to give another 20 seconds or so for folks to answer. Please go ahead and enter these into the chat once you have come up with what you believe the value is for the sensitivity. Okay, well, if I was to go with the sensitivity of our answers here, I would say the large majority of them are C's right now. And we actually have a pretty accurate prediction of the answer based on the folks' answers that are coming in. We do have 1 false positive, unfortunately, with the answers that came through. So what we're looking at here is, in our scenario, the algorithm identified 3 out of 4. So pretty simple fraction, 3/4. There were 3 true positives and 1 false positive, which provides a sensitivity of 75%. And what does this mean out in the real world? If there were 100 patients with disease, we'd find 75 of them. Okay. If there were 40 patients with disease, we'd find 30 of them. If there's 200, we'd find 150. We would be consistently finding, via the sensitivity, 75% of the patients that have the disease. What does this mean? How does it impact patients and providers? Well, a lower than expected sensitivity means we're missing patients. So if we had a number here that was sensitivity of 20% and we're missing 80% of the patients, the likelihood of anyone ever thinking that there was utility to our product is actually pretty low, right? Especially if we're far below the sensitivity of a provider that's looking at the same imaging. High sensitivity, conversely, means we're catching most of the patients with the disease. So if we had a sensitivity of 96%, for instance, we're catching 96 out of 100 patients that have that disease. That would be a very high value. An important concept I think that folks can remember as they're talking to providers and getting asked questions about things like sensitivity is we're not trying to exceed a provider's ability to do a diagnosis. We may find some that sometimes providers might miss. Providers will find some that AI might miss. Providers plus AI is a 1 + 1 = 3. Together, it's actually been clinically proven that AI plus providers have a higher level of sensitivity than either does uniquely alone in terms of being able to diagnose a disease. I hope you all enjoyed the lesson on sensitivity. We're going to move on to the next metric of sensitivity and try to keep the pace going. So specificity, we're going to move into opposite world right now. Opposite of sensitivity is actually specificity, a metric that focuses on how the algorithm performs against patients without a disease. So again, how the algorithm performs on patients without a disease. The definition is the proportion of people without a disease that have a negative finding. How often are our negatives right? As opposed to sensitivity, how often are our positives correctly identifying patients with disease? Specificity, how often or what proportion of patients is the algorithm successfully identifying without disease? A higher specificity means that an algorithm is labeling more of the true negatives accurately. Again, it's a pretty simple calculation. So if you go back and look at your sheets, you have the true negatives, we have the false positives, and it's really a simple division problem. So again, here's the scenario. We already created our chart. 4 of the patients actually have an LVO. There's 20 total patients, and we know that 3 times that there are false positives. And those are actually the values that we needed to calculate our false positives and true negatives of 3 false positives and 13 true negatives. So you ready for the big question, everyone? What is the specificity of this particular AI algorithm as defined? Now, I'll be honest and say that for me, specificity was harder to wrap my head around when I first started thinking about it than sensitivity was, because we don't often think about the impact of our non-findings. But this is, again, assessing performance against patients without disease. How likely were we to correctly identify them as not having disease via the algorithm? And the answer is D. 81.25%, 13 divided by 16 provides that value. We had 13 true negatives and we had 16 total patients that actually were negative. So moving on, what's the impact of specificity on patients and providers? Lower than expected specificity means that we're incorrectly identifying healthy patients that don't have a disease as potentially having a disease. In other words, we have false positives. We're not correctly identifying them as negatives. I think we all know the impact of too many false positives on providers. They're not happy campers generally when we have a lot of false positives. And when our false positives start exceeding our true positives, we start to get in trouble. And that leads to the next metric that we'll talk about, which is positive predictive value, which takes into consideration just the positive detections and the relationship between true positives and false positives. But before we do that, I forgot about this slide, which is that we're always trying to balance our sensitivity and specificity. There's trade-offs to this. Our ideal is that we want to pick an operating point right in the middle that's perfect for patients and providers, where we get the adoption we need, we get the value to the patients we're looking for. But if we optimize, we can always say we could optimize to 100% sensitivity or 100% specificity. I could say, hey, I just created a 100% sensitive algorithm. And how did I do it? I flagged every patient that is having a disease. I didn't miss a single one, right? But I flagged every single patient as having a disease. So I clearly had tons of false positives impacting my specificity. And then in inverse, I could say that there's no patients with a disease, and I would be 100% specific, 100% specificity. But I didn't create any value. So what is that balance that provides that operating point for the best experience for patients and providers? And that's what we're always trying to achieve here. Positive predictive value is our next topic. And I think this is actually a metric that is frequently misunderstood, as well as the impact of things like prevalence on PPV that we'll talk about in a moment. But what the heck is positive predictive value? The likelihood of a true positive when we flag a patient with an alert. So what is the likelihood that the alert that the user received is actually a true positive versus a false positive? What percentage of them are true positives of the alerts they receive? What is the probability that the patient actually has a stroke? PPV dramatically impacts provider experience. This is how they experience our product, is the PPV. If we have a low PPV, it means they're getting a lot of false positives and only a few true positives. If we have a really high PPV, it means that the alerts that they're getting are likely relevant patients with disease. I think one other thing I'll add, as I add a couple of examples in my notes here, a PPV of 10%, if we said our PPV is 10%, and we actually have algorithms that are in this category for really rare diseases, it means that 9 out of 10 alerts are actually going to be false positives. So if they're alerted 10 times, just one is likely to be a true positive. When we have a PPV of 80%, it would mean that 8 out of 10 alerts they receive are true positives. Obviously, much better performance and something that we would see on a much more prevalent disease. So what values do we need to pull out in order to understand PPV? We need our true positives from our chart, and we need our false positives from the chart. We called these out right in the description. 3 times we had true positives and 3 times we had false positives. So we have 3 and 3. This should be the easiest math of the day, I think, as it turns out. But let's figure it out. Let's calculate the PPV of this algorithm. And please put it into the chat when you have calculated it. I think we're all in agreement so far, so I hope you're all able to do this. We come up with a 50% positive predictive value. In simple terms, a 50% positive predictive value means there's going to be an equal number of true positives and false positives, 3 and 3. So if you're a doctor and you get 100 alerts over the course of 2 months, 50 of them are likely to be true positives. 50 of them are likely to be false positives. This may or may not be acceptable depending upon the acuity of the disease and the value to the patient of detecting this disease, right? So it's really going to depend a lot. That provider experience depends a lot on the value of actually finding these patients for the provider and the value to the patient of early detection of these diseases. So again, like, what does it mean for providers? So while we find there's different levels of tolerance, I just mentioned this for false positives based on the acuity and rarity of disease, the bottom line is it's a trade-off. Are they willing to accept the false positives to be able to view those true positives? We're taking a needle in a haystack without an AI algorithm, and we're making it into maybe an iPhone in a haystack. Still maybe hard to find, but it's in there somewhere and a lot easier to find than it would have been had it been a needle. Of course, we're always worried about creating anxiety with providers. Like, does this patient actually have a disease? Do I need to really look closely? Am I missing something? Am I crazy? That's what I worry about a lot with a lot of our products is, are we sometimes creating more time to review? And if we do, and if they find that to be regularly the case, the likelihood is that it will impact adoption. Providers may turn off their alerts. If they don't have their alerts on and they're not getting them from Viz, guess what? The patients will have delays to care. The patients will ultimately fall through the cracks. So this is always a metric that we're interested in trying to optimize. However, there's a lot of factors that play into it that we talked about a little bit already, and we'll talk about more after we go through the negative predictive value side of things. So negative predictive value, you may see a trend here. Again, negative predictive value is very similar to PPV, but this applies to the patients that do not have disease. So patients we expected not to have disease based on the algorithm findings. So these are This is a metric that looks at the patients that were the algorithm called negative or called nothing. In our case, we call it a non-finding, but it's similar to a negative finding, versus PPV, which is where the algorithm called a positive. So NPV is the likelihood that a non-flagged case is correctly called negative. So when we say it's not an LVO or not a PE, what is the likelihood that that is a correct assessment of the situation? So if a stroke is not detected, what's the probability the patient did not have a stroke? Calculating the NPV requires the number of true negatives. True negatives, so those where the patient didn't have a disease and the algorithm correctly identified it, and false negatives, where the patient didn't have a disease and the algorithm actually flagged that the patient may. So we call out a couple of metrics here on the bottom, false negatives, true negatives. False negatives, we had one miss that we're talking about, and true negatives, we decided, I think, was 13, if I remember right. Okay. So based on that, let's try calculating the negative predictive value of our algorithm, which are the true negatives, 13, divided by the true negatives plus the false negatives. We've got a lot of D's coming in, folks. And as it turns out, D is the correct answer due to math. We have 13 as our numerator and 14 as our denominator. There were 13 true negatives, 13 times where the algorithm didn't flag a negative study. And there was one false negative. One false negative that we identified. 13 divided by 14 is 92.86. So what's the impact of NPV on providers and patients? Lower than expected means that a significant proportion of the identified negative cases are actually false negatives. Nobody wants a bunch of false negatives. Those patients actually have a disease. False negatives are bad. We're going to have some. We are not a diagnostic product, but if we have too many, that could result in missing patients who actually have the disease, leading to potential harm. And the exciting thing is next we actually are going to talk about prevalence after we just talk one more time about the balance. So looking at balance, we're always trying to optimize, right? If we optimize for PPV, MPV is going to take a hit. If we optimize for MPV, PPV is going to take a hit. Likewise to sensitivity and specificity. Optimizing for sensitivity, and I trust you, if you think about these and talk about them enough, they do start to roll off your tongue. Decreases specificity, leading to more false positives, which decreases PPV. And optimizing for specificity will decrease sensitivity, leading to more false negatives, which decreases the PPV. And we're always trying to find that balanced operating point with our algorithms. In fact, in the past, we've actually released algorithm updates where there's no more training data added. All we're doing is actually optimizing our operating point. So disease prevalence, what the heck does this mean and how does it impact us? So first, we'll say what disease prevalence is. This is really a simple metric. It's just the rate of disease within an underlying population or a sampling of population. It doesn't affect sensitivity or specificity. Those are fixed numbers. Like those are values that we're shooting towards regardless of the prevalence of the disease. Those are in our FDA clearance. While we may see lower than expected results sometimes within certain customer data sets on sensitivity and specificity, prevalence does not impact them. It should not impact them. Prevalence is just prevalence. Prevalence does, however, dramatically impact PPV and MPV. If prevalence is high, PPV will be higher, plain and simple. A positive test means a higher probability of underlying disease, and the MPV will be lower. And if it's low, PPV will be lower, and MPV will be higher. So just because I had calculations for everything else, I wanted to throw our calculation of prevalence just to nail the point home on our scenario before. We won't have you guys do this because we're going to be running out of time. We said we had 20 patients that are being screened for LVO. 4 of them actually had LVO. Our prevalence of this is 20%. That's actually a high disease prevalence compared to pretty much every algorithm that we have in every real world scenario that we have today. Case study, the impact of prevalence. I could talk about this all day, but I want to provide a couple of examples just to drive the point home. I'm going to show you a couple of different examples where sensitivity and specificity are exactly the same, 90 and 90. So we don't have an algorithm that's exactly 90 and 90. This is an example algorithm, okay? All we're going to do is change the prevalence. The number of patients with disease is the only thing that's going to change as we walk through these particular examples. With a 10% prevalence, an algorithm with 90% sensitivity and 90% specificity, disease count of 100, which is a 10% prevalence, PPV is 50%. That's one true positive for every false positive. So every other alert they're going to get, it's going to be accurate. The MPV is super high. So the ability for it to adequately predict that a patient doesn't have disease would be really strong. Here's the provider experience: 90 true positives, 90 false positives, 10 false negatives, 10% prevalence. What happens when we put the exact same algorithm in a clinical study where half of patients have the disease and half of the patients do not have the disease? That is a 50% prevalence, where we ask a hospital for 200 patients with the disease, 200 without, 500 with, 500 without, whatever it happens to be. In this case, there's 1,000 patients. Half of them have a disease. That's a 50% prevalence. Look what happens to our positive predictive value. We are now at 90%. Let's go to another extreme and look at a 2% disease prevalence. Okay, so imagine we did a clinical study that showed a 90% PPV. This is great. And we need to do these because validation studies are critical. They help explain that we can successfully identify and rule out disease on a data set. With a 2% prevalence, PPV drops to 15.5%. Same algorithm, okay? Same algorithm, same performance. Suddenly, if we're talking about, this as an example, 98 false positives, 18 true positives. Think about that from an alerting perspective. This is approximately where we were with our first edition of aortic dissection, by the way. It was very close to this in terms of a 15.5% PPV. It was actually closer to 20%. But the experience for the providers was that they would receive somewhere around 4 or 5 false positives for every true positive. And they didn't like that, unsurprisingly. But that is with a 2% prevalence. And if I cut that in half to a 1% prevalence, it gets worse. PPV of 8.3%. That would mean that 91 out of every 100 alerts basically is a false positive. Same algorithm. The only thing I've done is change the prevalence of the disease across these metrics. Everything else is the same. This does not take into consideration scan quality or anything else. This is just prevalence only that we're changing here to show that the changes in PPV. So again, if you go back to that last time that a customer asked you, what's the PPV of an algorithm? These are things that we have to take into consideration. What is the prevalence? Is the prevalence at this hospital similar to what we see at other hospitals? Is this disease consistently the same prevalence? Is the clinical study that they were emailed showing one thing, but they're seeing another? Why might this be? And how could I help explain this to them? And how can I mitigate this from actually becoming a challenge once they actually turn the software on? What does it mean for our products today? I just threw in 90% and 90%. So this isn't the exact sensitivity and specificity for any of our current algorithms. But if we just took disease prevalences of 15%, 5%, 10%, and a teeny one, 0.5% maybe for HCM, with the same sensitivity and specificity, we see 61% PPV, LVO with stroke protocol. LVO with all head, we'd expect a smaller prevalence of disease relative to the total patients going through the algorithm. So just adding all heads, we'd see a lower PPV, but the likelihood is we're also going to catch some LVOs that might have otherwise been missed. That's the trade-off, right? And again, the PPV numbers are sort of made up here. They're just math. Might be a little bit different than what we see in the real world. So prevalence of 10% on PE could be a PPV of 50%. We're fortunate our sensitivity and specificity are a little bit higher than that. And then on an HCM type product, if we had a super rare disease where it was 0.5% prevalent in the population of, say, EKGs, we could see a PPV of 4%. A PPV of 4% would be 96 false positives for every 4 true positives.